Hello and welcome back to our course Data Analysis in Astronomy and Physics, the second part on probability. This part is about conditional probability, and as always, you find the subtopics on the right-hand side. We will introduce the concept of conditional probability, talk about Bayesian theorem, then discuss the influence and possible choices of prior probabilities, and finally present the Laplace rule of succession and demonstrate a few examples on that. Imagine that you toss a fair coin 3 times. What is the probability to get 3 heads? So we talked about this in the previous videos. The probability is 1 divided by 9. There are 9 possible outcomes. The favorable event is 3 heads. 1 out of these 9 outcomes, so the probability is 1/9. Now imagine that you already tossed the coin and you know that the last 2 results were head. What is the probability to get 3 heads now? Now there is no uncertainty with the last 2 outcomes. We only have to consider the first draw, and there the probability to get heads is 1.5. So depending on the condition that we know the previous results, we have some expert knowledge, our estimate of the probability is different. Generally, if 2 events A and B are independent, if the probability of one event is unaffected by the other, then it follows that the probability of A and B is the Generally, if 2 events A and B are independent, if the probability of one event is unaffected by the other, then it follows that the probability of A and B is the probability of A times the probability of B. So for example, you toss a coin twice. What is the probability to get 2 tails in a row? The probability is the probability of tail on the first toss times the probability on the second toss, which is 1/2 times 1/2 equals 1/4. The conditional probability is the probability of the event A given that we know B. This is written with this vertical bar and pronounced probability A given B, and this is the probability of A and B divided by the probability of B. A and B are 2 subsets of our sample space. B has already occurred, and therefore we are only interested in those events that are part of the intersection of A and B, and since B has already occurred, we have to make sure that all the events of A and B add up to unity. Therefore, we have to divide by the probability of B to renormalize. If A and B are independent, this reduces to the probability of A, because PA and B is the product PA times PB. We divide this by PB, and we have PA equals PA, which is true. If we have several possibilities for B, our formula consists of the individual subsums of PA given PI times PBI. A might be the parameter of interest, while the BIs are not. Knowing the individual probabilities PBI, we can get rid of them by just summing all the individual conditional probabilities up. The summation or integration is called marginalization. Let's have a look at an example. Let's say we have an urn that contains 100 balls. 70 balls are made from wood, 30 are made from plastic. 25 of the wooden balls are red, 45 are green, and 10 plastic balls are red and 20 plastic balls are green. So we can define the following events. Event A ball is made from wood. A bar or a complement, a ball is made from plastic. Event B means the ball is red. Complement B or B bar means the ball is green. Summarizing this setup in the following table gives us the probability PA of 70% because 70 from 100 balls are wooden balls. PA bar 30%. These are the 30 balls made from plastic out of these 100 ones. We have the 35% probability to have a red ball, which is the sum of the 25 wooden red balls and 10 plastic red balls. We have 45 green plastic balls, 20 green, 45 wooden balls, 20 plastic balls, which gives us a 0.65 probability. These sums nicely add up to 1, which means we covered the full probability space. Another possibility to visualize this setup is given in a tree. This is kind of a decision tree. When we draw a random ball, there are two options. It can either be made from wood with 70% probability or made from plastic. We are then here. If it's made from wood, the probability that it is a red ball is 25%. The probability that it is a green ball is 45%. And so on for the other cases. The probabilities that a ball is red, given that it is from by a certain material, is here denoted PB given A, PB bar given A, and so on. We can quantify the probabilities, these conditional probabilities, using the definition of the conditional probability that we had on the previous slide. We know that PB given A is PA and B divided by PA. So PA and B is 5 divided by 20, here on the bottom left. We divide this by the probability of A, which gives us 0.36. And we can do this for all the branches here on this probability tree. And we always have to make sure that all the subsets here, we have two possible options. So the probabilities here have to add up to 1. We have two options here. These two probabilities have to add up as 1. These two have to add up as 1. And of course, the final probabilities also have to cover our full sample space and add up to 1. Now imagine that you draw a red ball, but you are not being told its material. So what is the probability that it is made from wood? When we go back to the previous slide, we computed the probability of a certain color given the material. Now we have the opposite situation. What is the probability of a certain material given the color? We are not looking for P given A, but for the probability of A given B. So how does it relate to the probability B given A from the previous slide? We can write down by just using the formal definition that PA given B is PB and A divided by PB. And we can then expand the denominator and say PB is the sum of PB and A and the probability of PB and A complement. So these are and we know this probability already. This is the 25%. And we know these individual ones, and which means we can compute the probability of A given B by 5/7. And we can do this also for the other branches. What we did is that we calculated the inverse probability, which is also called the base probability.